Hello, and welcome to my talk. My name is Susan Holmes, and I work at Stanford. I'm a professor of statistics, and I'm going to talk to you about uncertainty quantification for nonlinear, nonparametric dimension reduction. This is joint work that I've done with some of my graduate students in my lab, in particular Lan Nguyen helped me with the nonlinear uncertainty quantification. And I also worked with a postdoc, Sergio Pacalado, on some of the non-parametric. So first of all, I'm going to talk about the geometry of data. And in looking at different data sets in high dimensions, usually we consider that we have points. So these were the sample points or the observations that we see, and they're in p dimensions. When we say high dimensions, generally p is large. In biology data, the n can be quite small. So we often add distances through weights, and we have inner products. So we have two geometrical spaces. Here we have the observations who actually have different weights, and that's possible. Here we have the variables as they appear in the space of observations. So one of these perspectives is the dual of the other. So we have data with p variables and then observations. We often have matrix of weights. Those are like the bubbles that I showed you. And then we have a weight on the variables. So we have two Euclidean spaces, one with an inner product with regards to the weighting of the variables and the other weighting on the observations. Generalized principal component analysis is very often the first step that we do. It's a linear method which enables us to insert different weights which take into account some data that we have. It can be the case that you can organize these weights in a commutative diagram. And in this commutative diagram, we have what we would call the variance covariance matrix V. And if you multiply V by Q, that would be the equivalent of taking x prime dx and then Q. That's going around the diagram in one direction. You could also go around the diagram in the other direction. That is, start off, say, x, q, x prime, and then d. So there are two ways of going around. And the fact that the diagram commutes is a duality principle, which tells us that whether you take the eigen decomposition of VQ or of WD, they have the same eigenvalues. And this is really important because very often one of the dimensions is small and the other is large. So we never have data where both n and p go to infinity, but when one of the two indices, so say p becomes very large, it's enough to look at the dimension n and look, say, at the data by the Gram matrix, which is n by n, and that's smaller, and that will be low dimension. So as I said, the first step that we usually do is to do principal component analysis and take the eigenvalues and the eigenvectors and look for a low dimensional representation. Now it turns out that this is actually equivalent to looking at the RV coefficient of the lower rank diagram with the original one, and trying to find the low rank approximation, which gives us the highest RV coefficient, which is a multi-table correlation coefficient based on the Frobenius inner product. So the definition of this is the trace of the O prime 1 T transpose O2, and then we have a normalization term that we take the square root of. This is very much like what happens in the ordinary correlation coefficient, where you take square root of the variances. So here the RV coefficient serves as a way of comparing two PCAs, for instance, or two different decompositions. I'll show you a little application and how we use it. One of the difficulties in doing dimension reduction is uncertainty quantification in low dimensions. We want to know how well each of the sample points, for instance, is projected. So this is from a paper called 10 Quick Tips on Dimensionality Reduction that appeared in PLOS Computational Biology with Lang Huang Yan. And we made plots where we were looking, here this data was actually low rank. So in this case, we didn't have a lot of components in the signal. If you have many more components, then there's more uncertainty in the projections, but you can still see a very clear localization. Now, in order to make that localization appear clearly like this, we actually had to do some pre-processing of the data. That is, you can't just bootstrap and compute the contours. And you can't create Bayesian posteriors and just create the contours of uncertainty in high dimensions. You need to align everything because, first of all, when you take a PCA, the signs are not unique. And also the first and second eigenvectors might switch if they're close. And so you'd end up with convex hulls like this. And that would be meaningless. And so we do this alignment. That's what the RV coefficient serves to do. And the alignment is done by taking the whole matrix of inner products, the RV coefficients, and taking the first eigentable or eigenmatrix by taking the first eigenvector of this RV coefficient matrix. Now, we've seen that, you know, this duality of the data, we can choose which is the best dimension. The P by P matrix might not be the best choice if you have 25,000 features. It might be better to take the N by N. And we can see that we use an angle between operators to create a consensus. Now we're going to use this same method for doing multidimensional scaling. And multidimensional scaling reverses in some sense in Euclidean embedding given a distance. So suppose that we go backwards from, we're given a distance delta between all the sample points, so it's n by n. We take the square and we recenter. We're using the recentering matrix on the left and on the right. And we take this matrix B, and that one will give us the best approximation in some sense. We can do the eigen decomposition of B, and that's standard multidimensional scaling. So here the algorithm diagonalizes B, we find the principal coordinates, and then you choose how many eigenvalues, and that gives you a approximate Euclidean embedding. Now, very often when we look at real data, the embedding shows very strong nonlinearity of the data. And so this is an example where we have a gradient which is due to urbanization in human microbiome data. That occurs very much. And so we have data on manifolds that we're trying to summarize instead of having data on planes. Here's another gradient in a paper that appeared and which also has R package called BUDS that was written by Lan. And in that paper, we actually quantify the uncertainties of the different points by contours in exactly the same way I showed you how to do uncertainties for PCA. But in this case, our work, our basis, our foundation for the work is on the distances between the points. And one of the things that we know when we see the data is that if there are many points in a neighborhood, we're more sure about the distances between the points than if we have a very sparse neighborhood. So the data are not uniformly distributed along the manifold, and so in the case of just one dimension, you saw how there were gaps, but that can happen in higher dimensions. And so what we do is we project, we go and look at changing the metric to take into account the change in uncertainty in the manifold area. And so this is done by working, as I said, on the distances. And here we did a Bayesian method. So we took the distances and we estimate the local variances. And from these local variances, we create a Bayesian hierarchical model. And here this gives us our local standard deviation. And we've used Stan in order to create the contours. So we made a change, a slight transformation of the data. And then we have Cauchy for the parameters. And the estimation of the standard deviation is done looking at local neighborhoods. So it's a local method, so it allows for nonlinearity. Here's the fit, and here is the output, as I showed you before. So more general, I'm going to point you to another application of this method of aligning the data, although I don't have time to go into the detail. This was actually done using UMAP, which is a generalization of this one-dimensional method to several manifolds. And this also uses a change of distribution. And so for the full Bayesian nonparametric model, this is work that appears already in the Bayesian nonparametric coordination analysis of microbial communities in JASA. And again, we had a whole set of draws from a posterior distribution with parameters that we had to align. And again, if you didn't do the alignment, you got something which wasn't well represented. So you have to do this same registration that we did with the RV coefficient. And in the end, you get alignment where you can see the uncertainty contours. Thank you very much for listening to me. Here there are packages and resources, and these two were written by Lan, and here's Lan here. This is my whole lab. We work on high-dimensional biological data, and we're funded by the NIH and the NSF. Thank you very much.